Okay, here's a quick review of the stoichiometry map notes for those of you that missed it or just need a refresh. Okay, so we're looking at this map and we have used versions of this map before, right? When we first learned our molar conversions, we just used the left-hand side of the map, remembering because we only worked with one molecule. So we were only working with O2 or we're only working with H2 or whatever. And so if I had liters of H2, I could figure out how many moles of H2 I have or how many grams of H2 I have, as long as I first converted it to moles. So that was what we very first learned and we kind of covered in our 3.1 test. And then on Friday, what we looked at was this new way of converting moles of one molecule to moles of another molecule based on a balanced equation. So we could go from grams of, say, oxygen to moles of hydrogen based on the balanced equation, right? So we worked on either being given something from over here, converting it to moles to figure out how many moles of the other compound there was. And then some of our questions from Friday didn't start on the left, it started in the middle. So you were given moles of, say, oxygen, and you were asked to figure out how many grams of hydrogen or liters of hydrogen it was. So you went from moles of oxygen to moles of hydrogen and then solved for whatever your conversion was here. This is nothing new. So these are our same conversion factors. I just wrote them as fractions. Remember, you can write them the other way too because they're equal, right? So I've got 1 mole is equal to the molar mass of any compound. 1 mole is equal to 6.02 times 10 to the 23rd particles. 1 mole is equal to 22.4 liters of any gas. And so I rewrote those. Remember that molar mass does change based on the compound. So you do have to calculate that. So that one's always kind of a pain. You have to figure out your molar mass before you can move forward with your equation. But these are things that we've already learned, and we're just taking this into a 4-step or 5-step plan instead of just a 3-step plan that we looked at on Friday. So let's figure it out. So the one thing that we added in, the additional thing that we added in was identifying if there were any unit conversions needed. So that's going to be something that we'll look at in our second example. We'll talk about that in just a minute. So remember, our plan is always to identify your given in your problem and then go identify your last step. Then you're going to evaluate this time. So you're going to evaluate, are there units that aren't a unit that's our standard conversion? So are we giving kilograms? Well, kilograms are not part of our conversions. We can convert grams to moles from our molar mass, but we are going to have to convert kilograms to grams within our equation if that's the case. Same thing if we have like a unit of liters. So if I have milliliters, a milliliter is smaller than a liter. So I'm going to have to convert that milliliter value to a liter value before I can move forward in my equation. Once I know my beginning and my end, I'm going to figure out my middle. My middle is always going to have moles in the very center, but occasionally I might need a unit conversion either before or after the moles. So just things to think about. So here we're given a balanced equation, and it says how many grams of O2 are used to produce 0.72 liters of carbon dioxide. So our value is here, our actual numerical value, so that's our given, and that's what we start our plan with, 0.72 liters of carbon dioxide. Then the next step is to know where we're going, right? So the very next thing you do is write the last part of your plan. You'll have a blank space here, grams of oxygen. Then we're going to evaluate, is liters, what we're given, something that's part of our molar conversions? Yes, liters are part of our molar conversion. We have moles to liter conversion. Are grams part of a molar conversion? Yes, We have a molar mass in grams conversion to moles, so that is not a problem. We don't have any additional conversions to do. So we're just going to go from liters of carbon dioxide to moles of carbon dioxide, from moles of carbon dioxide to moles of oxygen, and then from oxygen moles to oxygen grams. That's our plan. Remember, we learned on Friday that our plan then turns into our numerators of our equation fraction. So we copy this exactly as given, 0.72 liters, and then these are our units. We'll figure out our values in a minute. So moles of carbon dioxide goes here, moles of oxygen goes here, grams of oxygen goes here. So those are my 4 fractions for my equation, and I have my units. The next thing that you want to do before you start trying to plug in numbers is figure out your denominator units. We never have a denominator unit for our first fraction. It's always just something over 1. So we take this numerator unit and turn it into our denominator unit over here so that we can cancel it out, right? So liters of carbon dioxide is what I start with. That turns into my denominator unit here. And then moles of carbon dioxide here turns into my denominator unit on the next fraction, moles here. And then finally, moles of oxygen turn into my denominator here. What that does is it allows me to eliminate my units, right? So I can eliminate liters because there's 1 on top and 1 on bottom. I can eliminate moles of carbon dioxide because there's 1 on top and 1 on bottom. I can eliminate moles of oxygen because there's 1 on top and 1 on bottom. Now what I've successfully done is only left with grams of oxygen, which is our goal, right? So we have set this up properly to eliminate all units besides grams of oxygen and be able to calculate the numbers appropriately. All right, so let's look at what we have then. So now that we have our units, we have to figure out what our values are. 7.72 is given, that's always over 1. Moles over liters, it's always 1 mole is equal to 22.4 liters. Moles over moles, remember we get our mole over mole values from our balanced equation, the coefficients in our balanced equation. So our coefficient for O2 is 5, so 5 oxygens. And our coefficient for CO2 is 3, so we put 3 in right there. And then we have a grams to moles conversion. So our molar mass of O2 is 32 grams per mole. Remember, that's because oxygen's atomic mass is 16, and there's 2 of them. So we got 32 grams per mole there. We multiply across, we get 115.2 over 67.2. That reduces to 1.7. Remember, your final answer needs to have your units in it, so 1.7 grams of O2. Let's look at our second example. Okay, I'm a little disappointed that my color didn't come in on this, so I hope you guys can kind of see the difference between my plan and my equation, but we'll go there. Okay, so we have 2 in our balanced equation here, 2 molecules of potassium chlorate decompose and turn into 2 molecules of potassium chloride and 3 molecules of diatomic oxygen, so O2. How many liters of oxygen are produced if 0.346 kilograms of KClO3 decomposed at standard temperature and pressure? So, first of all, our given is 0.346 kilograms. Our answer is going to be liters of oxygen. So that's where we start in our plan, 0.346 kilograms. We're going to end up with liters of oxygen. Then step 2 in our plan, step 3 in our plan, because step 2 was to come up with our endpoint, was to consider our units. So in this case, we have kilograms, and our molar conversion is grams to moles. So I'm going to have to go from kilograms of potassium chlorate to grams of potassium chlorate. Once I have grams of potassium chlorate, I can now go to moles of that same compound. And then when I have moles of that compound, I can convert to moles of another compound, moles of O2. And then for moles of O2, I can go straight to liters of O2 because that's a standard unit in our conversions. So that right there then is our plan. There we go. Okay. And so now we're going to take our plan and we're simply going to write it into our numerators. I knew I was going to run out of room here, so I kind of scooted it over. So, but my 0.346 is going here. My grams of potassium chlorate right there. Moles of potassium chlorate right there. Moles of O2 right there. Liters of O2, the end of my equation. So I set that all up exactly as I wrote it. Then again, I just did the same thing that I always do and use my dimensional analysis rules. I take my units from my numerator and turn them into the units of my denominator for my next fraction, right? So kilograms of potassium chlorate go right here. Grams right here. Moles right here. Then I switch to moles of oxygen right there. So that means I've eliminated this. I have eliminated this. I've eliminated this. And I've eliminated this. So I'm just left with my units that I need in my answer, which is liters of oxygen, right? So I've set that up properly. And now I also have an appropriately set up equation to know how to plug my numbers in. So let's look at those numbers that we need to plug in. I've got grams over kilograms. There are 1,000 grams in a kilogram, so that's your number here. Of course, you start with your given. Sorry, I got ahead of myself. So 3.46 over 1. 1,000 grams in a kilogram. Moles to grams, remember that's 1 mole to the molar mass. You can see over here, I have calculated the molar mass of potassium chlorate. So you can see how I did that. We learned how to do that a while ago. So quick math done for you, 122.5 grams per mole on that one. My equation up here provides 2 as my coefficient for potassium chlorate, 3 for my coefficient for oxygen. So I assign them appropriately. 3 moles of oxygen created for every 2 moles of potassium chlorate consumed. And then I have my liters over moles. That's the easy 22.4 over 1 mole conversion there. And then I just do my math, multiplying across all my numerators, 0.346 times 1,000 times 1 times 3 times 22.4 gives me a pretty big number, 23,251.2. 1 times 122.5 times 2 times 1 is 245.1. When I reduce that fraction, I get 94.9 liters of oxygen. So I hope that was helpful. Remember, you want to do your plan first. Turn that plan into the numerators of your fractions for your equation, and then use the units of the numerators to set up the units of your denominators. Once you do that, then everything else is either conversions that you should already have memorized by now, or simple information that you're picking out from a balanced equation. The only thing that's tricky is when you have to add up that molar mass there. So I hope that's helpful. Good luck on your practice problems.